let's talk briefly about the idea of a transfer function. Transfer function, again, is something for an LTI system. So just like the impulse response was for LTI systems, in other words, yeah, you could define an impulse response for any system. It wouldn't be that meaningful. Similarly, a transfer function is meaningful for LTI systems and not so meaningful for anything else. And what this is the Fourier transform of the impulse response. So, of course, since the Fourier transform is invertible, then you could equally well say that the transfer function fully characterizes an LTI system. Okay, so h of f equals Fourier transform of h of t. Same thing in discrete time, right? Okay, now what does the transfer function mean? Well, because a system in time, an LTI system, is always doing a convolution, all right, then that means in comes x of t and out comes x of t convolved with h of t. Well, here we get to put everything together that we've learned. We know that an LTI system does convolution, and we know that convolution is best understood in the frequency domain because of the convolution property. So if we put everything in the frequency domain, we say x goes in, but I'm going to represent it as a capital X of f, and my system has a transfer function h of f, then what comes out is just a product, x of f, h of f. So in the frequency domain, an LTI system is very simple. This is all it does. H of f describes, essentially you can think of it as how much each frequency gets amplified or attenuated. And so your input signal comes in, each frequency gets rescaled. Of course, each frequency also can have a phase added to it, because multiplication means phases add, and then it comes out with that change. So LTI systems now are very simple to understand now that we can think of them in the frequency domain. One feature of them that's worth noticing is that sinusoids are, well, complex exponentials are what we call eigenfunctions of LTI systems. What that means is if you put a complex exponential into, let's say, e to the I 2 pi, I'm going to use a capital F just to say that that's a constant for number, times t. So here's a complex exponential signal. If I put that into an LTI system, what comes out, and the eigensignal or eigenfunction means that what comes out is the same thing times a constant. Let's just say that's capital A for our constant, could be complex, e to the I 2 pi f t. Now notice this constant, if it has a phase, that's going to amount to shifting our complex exponential. If it has a magnitude, it's going to amount to scaling it. Now, the magic is that any LTI system will have this property that a complex exponential in gives you the same complex exponential out at the same frequency, but with a scaling parameter. So this is called the eigensignal, and this is the eigenvalue. Now, let's argue that that's true and figure out what A is. A couple ways to do that. You could use what we already said. You could think of this in the frequency domain, and this is the way that Longines described it in the Piazza note. He said, take this to the frequency domain. This is just a delta function in frequency. Then you do multiplication here, and you take it back to the time domain. I'm going to do it in a more direct way. Let's just write out convolution, and by the commuting rule, I'm going to put it backwards here. E to the I 2 pi f t convolved with h of t. All right. I'm going to write the integral, but I'm going to put the h first just by my preference. Again, it commutes. H of tau e to the I 2 pi f t minus tau d tau. Now, this is an exponential function. I can split that sum into two different terms. I'm integrating with respect to tau, so I can take the part of t out. So that equals e to the I 2 pi f t times this integral, and you notice two awesome things here. First of all, you notice that t only appears one place in this equation. I'm going to put parentheses here so we can see it. Everything in the parentheses does not have t in it, so that's just a number. Now, so the signal is this complex exponential. Therefore, we've, in a very simple way, argued that you put a complex exponential in, you get the complex exponential out. So it is indeed an eigensignal. But more interestingly, we've just sort of derived the Fourier transform equation. We didn't even use it. We didn't pull it out of anything. I mean, we didn't say, let's apply the Fourier transform here. But that is the Fourier transform equation evaluated at the frequency capital F. So this is exactly, I'm going to put that part first, h of f times e to the I 2 pi f t. So what is the eigenvalue? This is the eigenvalue. It's h of f. All right, so if we had never seen the Fourier transform, we would have just derived that this Fourier transform is useful because it tells you the eigenvalue for each frequency, okay, as a function of frequency. That's great. Now, in your problem set, you did this for real signals, and you said, okay, forget about these complex exponentials. Let's say I live in a simple world, the real world, where everything is real. Let's assume that h of t is real, because it's a real system, all right? And let's then put in a real sinusoid, so cosine of 2 pi f t. Well, now, to calculate what happens, you have to do some work, and you've already done it in your problem set. The easiest way is split that into two complex exponentials, handle them each separately, and use linearity. The bottom line is you get the magnitude of h of f out front. That's the scaling factor for the cosine. And you get the phase right in here, phase of h of f. So your cosine gets shifted by the phase of the Fourier transform, and it gets scaled by the magnitude. So that's also a really nice way to remember what this transfer function is, because h of f is the transfer function. It's the Fourier transform of the impulse response. We have many ways of understanding what it does and what it means.